I want to start today by putting you in a bit of a high-pressure situation, a thought experiment. Imagine I kidnap you. Don't worry, this is purely hypothetical. And I drop you onto a remote island or maybe a foreign country where you don't speak a single word of the language.
Okay, I'm picturing it. Panic is definitely setting in.
Good, hold on to that panic. Here are the rules. You have no textbook. You have no dictionary. You have no teacher. You don't even have like a picture book to point at things. You are completely cut off from any learning resources. All you have is the raw sound of people talking all around you.
It's the ultimate immersion nightmare.
Exactly. But here is the catch. You cannot leave this place until you have mapped out the entire grammatical structure of their language. You need to figure out the syntax, the rules, what's a noun, what's a verb, and how they all connect, to create meaning just by listening.
You are describing a scenario that would make most linguists break out in a cold sweat. But you're also describing the fundamental problem of unsupervised learning in AI.
Right. And arguably, if you can solve that puzzle, you've basically cracked the code of human language itself.
It is the holy grail of the field. Absolutely.
And that is the cliff edge we are standing on today. We are doing a deep dive into a really fascinating paper titled Unsupervised Dependency Parsing via Grammar Induction and Lexical Precedence. It's by a team of researchers, Hiram Calvo, Omar Gambino, Alexander Gelbook, and Kentaro Inui.
And what makes this paper stand out is just the sheer audacity of what they attempted. They developed a system they called DIUETTGI, and their mission was to see if a computer could learn the structure of sentences, what we call syntax analysis, without the trust fund that most modern AI systems rely on.
Trust fund. I like that description. You're saying most AI is born rich?
In a way, yes. I mean, if you look at the heavy hitters, the best language parsers out there for English or Chinese or Spanish, they are what we call supervised. They are born into a world of massive resources.
Okay, let's unpack that before we get to the new stuff. When you say resources, what exactly are we talking about?
We're talking about tree banks. And no, that's not a financial institution for squirrels. A tree bank is a massive corpus of text, thousands upon thousands of sentences, where a human linguist has manually, painstakingly tagged everything.
So a human actually sat there and labeled every single word.
Every single word. They label the nouns, the verbs, the adjectives. But it's more than that. They draw the connections. They explicitly tell the computer, this word is the subject, this word modifies that word, this is the object.
So the computer isn't really figuring anything out. It's just
memorizing.
It's just memorizing the answer key.
Precisely. It's pattern matching against a massive pre-existing answer key. And don't get me wrong, it works. For languages like English, supervised parsers can hit over 90% accuracy, but there is a huge downside.
The cost.
The cost, the time, and the sheer human effort. Building a tree bank for a single language takes years. You need teams of PhDs to agree on the structure of thousands of sentences.
Which means if you are a language with a smaller population, or just a language that, big tech companies don't prioritize, you're out of luck. You don't get the cool AI tools.
Exactly. You're left behind. And that is the bottleneck of supervised learning. We simply cannot manually tag every language on Earth.
So we need the Wild West approach, unsupervised learning. The goal is to just throw raw text at a machine and say, figure it out yourself.
That is the dream, creating a dependency analyzer for pretty much any language without needing those years of manual tagging.
Now, the authors of this paper, Calvo and his team, they're tackling this unsupervised challenge. But they admit right up front that going in like 100% blind is just too hard. The failure rate is too high. So they propose a middle ground, a kind of hybrid approach.
Right. They don't give the computer the answer key, but they do give it a scaffold. They decided to include morphological information before the learning process begins.
Which sounds technical, but it basically just means they tag the parts of speech.
Yeah. Correct. They use a tool, in this case, something called the TNT tagger, to scan the raw text and assign labels. Noun, verb, adjective, preposition.
Okay, but hold on. Isn't that cheating? I mean, if the goal is unsupervised learning, why are we giving it tags?
It's a fair question. But think of it this way. Imagine I asked you to build a Lego castle, but I gave you a pile of random plastic shards, some of which weren't even Lego pieces. That's raw text.
Impossible.
Now imagine I give you the same task, but I've pre-sorted the pieces. I tell you, these are the standard bricks, these are the flat plates, these are the slanted roof pieces. I haven't told you how to build a castle, but knowing what the pieces are makes the structural analysis exponentially easier.
Okay, that makes sense. So they aren't teaching it grammar rules, they're just identifying the building blocks.
Exactly. And the TNT tagger they used is a statistical tool that's about 94% accurate. So right out of the gate, the computer has a decent map of what the words are.
Let's look at the experiment. Phase 1, the setup. They took a corpus of text, the key ST3LB corpus, which is Spanish.
And to simulate that alien planet scenario we talked about, they stripped out all the existing grammatical information. They treated it as raw text, applied the tags, and then fed it into the black box.
This is the grammar induction phase. They used two tools here with great sci-fi names, ABL and Emil.
ABL and Emil. They sound like a folk music duo from the 60s.
They really do. But they work very differently. Let's dig into ABL first. Alignment-based learning. How does this actually work? Because the paper mentions it uses a greedy algorithm.
So ABL is based on the concept of substitutability. It assumes that if two sequences of words can be swapped out in the same sentence structure without making the sentence gibberish, they'd probably play the same grammatical role.
Give me a concrete example.
Okay, take the sentence, the red car is fast. Now take another sentence, the blue truck is fast. ABL lines these up, that's the alignment part, and sees that the red car and the blue truck are in the exact same position relative to is fast.
So it groups them.
Yes. It assumes the red car is a chunk, a constituent. It learns these chunks by brute force comparison across the entire text. And the greedy part means it's opportunistic. It just grabs the first, best alignment it finds to build its library of chunks rather than trying to calculate every infinite possibility, which would take forever.
Okay, so ABL is the swapper. It learns by seeing what fits in the same slot. What about Emil?
Emil is a bit more nuanced. It focuses on context. It looks at a word or a phrase and analyzes the environment it lives in, the words to the left and the right. It stores these context expression pairs to derive its rules.
But in this specific experiment, Emil didn't do so well.
No, it struggled. And that highlights a huge issue in AI. Data hunger. Emil generally needs massive corpus, we're talking 100,000 sentences or more, to build enough statistical confidence in those contexts.
And the Spanish corpus they used was not that big.
It was tiny, about 300 to 700 sentences.
Wow, that is microscopic in the world of big data.
It is. And that's why ABL won this round, because ABL is a greedy, alignment-based learner. It could actually function with that small data set. It could find the swappable patterns even with limited examples, whereas Emil was just starved for data.
So they run ABL. The machine compares the sentences, finds the swappable parts, and puts brackets around them. It gives us what they call a shallow parse.
Right. A shallow parse basically groups the words. So instead of seeing 4 separate words, the red car stopped, it sees the red car as one unit and stopped as another.
And this is the crux of the problem, just knowing that the red car is a group isn't enough, is it?
No, it's not. That's what we call constituency parsing. It tells you who is sitting at the same table, but it doesn't tell you who is paying the bill.
We need dependency parsing.
Exactly. Dependency parsing draws arrows inside the circle. It tells you the relationships. It tells you that car is the main word, the head and red and the are modifying it. They depend on it.
If I just have the brackets from ABL, I don't know who is in charge. I just know they hang out together.
Correct. And computers are notoriously terrible at guessing who is in charge without being told explicitly.
So this brings us to phase 2. This is the core innovation of the paper. They needed a way to tell the computer how to find the head of a phrase without writing a million complex grammar rules.
And their solution was, it was brilliantly simple. They created a hierarchy. They call it the lexical categories precedence system.
Which is a very fancy way of saying the corporate ladder of words.
That is the perfect analogy. They decided that instead of complex linguistic analysis, they would just strictly rank the parts of speech. They made a list. If you are in a group of words, the word with the highest rank on that list is the boss, the head. Everyone else works for that word.
That seems suspiciously simple. Does language really work that way? Can you really just rank words like a tennis tournament?
Well, let's look at the ranking they discovered for Spanish. They defined 12 ranks. Who do you think is number 1, the CEO of the sentence?
I remember this from the notes. It's the verb.
The verb. And this actually aligns with a lot of heavy linguistic theory. Dependency grammar often views the verb as the root of the entire thought. The action drives the meaning. Without the verb, nothing happens.
Okay, so verb is number 1. If there's a verb in the chunk, it's the head. Who is in number 2?
This is where it gets interesting. and where you might raise an eyebrow. Rank number 2 is the adverb.
Wait, really? An adverb beats a noun? That feels wrong. If I say runs quickly, runs is the verb. Okay. But if I say very fast car, actually, wait, that doesn't have a verb.
Think about the structure. Adverbs modify verbs, adjectives, or other adverbs. They are high-level modifiers. In the hierarchy they built for Spanish, the adverb takes precedence over the noun.
So noun is number 3.
Yes, noun is number 3, followed by adjective at 4, pronoun at 5.
And all the way at the bottom.
Punctuation is number 12. The intern getting coffee.
So let's trace the logic. The algorithm looks at a chunk like the red car. It checks the tags. The is an article rank 9. Red is an adjective rank 4. Car is a noun rank 3.
And because noun, rank 3, is the highest rank present in that specific group, car becomes the head. The arrow points from car to red and from car to the young. Boom, you have a dependency tree.
It's basically top trumps for grammar. My noun beats your adjective.
It is. And the beauty is they stripped away all the details. The TNT tagger gives you rich data. It tells you if a verb is plural, singular, past tense. The researchers ignored all that for the hierarchy. They just said, is it a verb? Yes. Then you're the boss.
They cite a linguist named Hengeveld to back this up, don't they? This wasn't just a random guess.
Right. Hengeveld's work on functional grammar suggests that there's a strict hierarchy in how languages are built. The authors are betting that this hierarchy is universal enough that you don't need complex probability math to find it. You just need the ranking.
So we have the chunks from ABL. We have the hierarchy to sort the chunks. Now we hit phase 3, the moment of truth. Did it actually work?
They tested it on the Spanish corpus first. They measured precision and recall.
And the numbers were, well, let's be honest, they weren't 95%.
No. Precision was 32.3%. Recall was 31.8%.
I have to play devil's advocate here. If I came home with a 32% on my report card, I'd be grounded for a month. Why should we be impressed by this?
Context is everything. You have to look at the weight class they are fighting in. They ran a comparison with a commercial system called Connexer.
And Connexer is the trust fund kid we mentioned earlier.
Exactly. Connexer is a state-of-the-art semi-supervised commercial analyzer. It uses dictionaries, pre-programmed rules, syntactic annotations, the works. It has millions of dollars of development behind it.
And what did the $1 million Connexer score on this task?
Between 40 and 42%.
Wait, so the expensive, rule-heavy commercial system only got a 40%?
On the specific raw text task, yes.
Mm-hmm.
And our scrappy little unsupervised system using nothing but a tagger and a simple ranking list got 32%.
They were within 10 points of the Goliath.
That's the key takeaway. They achieved comparable results, or at least results in the same ballpark, with a fraction of the resources. It proved that the hierarchy idea wasn't just a guess. It was capturing something real about the language.
But they didn't stop there, and this is the part I really want to highlight, because the critique of unsupervised learning is often, oh, it only works on the one data set you tuned it for.
Right. Overfitting. So, to prove this wasn't just a Spanish thing, they decided to build an English parser.
And the paper mentions they did this in a few days.
Which is unheard of. I mean, usually building a parser for a new language takes months or years. They just took the Suzanne corpus, about 7,500 sentences of English, and applied the same method. But, and this is crucial, they had to tweak the ladder.
The corporate ladder had a shakeup.
A little bit.
Uh-huh.
Languages share deep structures, but they aren't identical. In English, they found they had to prioritize auxiliary verbs.
You mean words like is, have, do the helping verbs.
Right. So the English hierarchy became verb is still number 1, but number 2 became auxiliary verb. Number 3 was the auxiliary itself, then noun at number 4.
So they inserted a layer of middle management between the verb and the noun.
Very bureaucratic. But it reflects how English relies so heavily on those helping verbs to construct tense and mood.
And how did the English version perform with this tweaked hierarchy?
Better than the Spanish one. Precision was around 39%. The F-score was 40%.
That's basically matching the commercial Spanish system's performance.
It is. But here is the real comparison that matters. They compared their results to a study by Cohen et al., which is considered state-of-the-art for unsupervised learning.
And Cohen used, let me guess, very expensive math.
Extremely. Cohen used Bayesian parameter estimation. It involves complex probabilistic models, heavy computational load, estimating parameters over millions of iterations. It's the rocket science approach.
And Cohen's score?
40.5% precision.
And our guys, using a simple list that says verb beats noun, got 39%.
39%. They essentially matched the state-of-the-art results of complex Bayesian math using nothing but a sorted list of word types.
That is the aha moment for me. It validates that simplicity can compete with complexity if the underlying theory, the linguistics, is sound.
Exactly. It shows that language isn't just a bag of random probabilities that you need a supercomputer to calculate. It has a rigid backbone, a skeleton. If you know what the bones are, the hierarchy, you can reconstruct the animal without needing to analyze every single cell.
So let's zoom out. We've geeked out on the algorithms and the rankings, but what is the so what here? Why does this matter to the person listening who isn't building a parser in their basement?
It matters because of the democratization of technology.
Yeah.
We talked about the trust fund problem at the beginning, how low-resource languages get left behind.
Right. If you speak a dialect with only 500,000 speakers, Google isn't building a tree bank for you.
Exactly. Nobody's going to spend $10 million tagging data for a language with no commercial market. But this method changes the economics completely. It says, give me raw text, which you can scrape from the web. Give me a basic tagger, which is relatively easy to build. And give me the hierarchy.
And since the hierarchy seems to be mostly universal, you just need to tweak it a bit. Maybe swap the adverb and noun, add an auxiliary layer.
Precisely. You can build a functioning parser for a low-resource language in days, not years.
It lowers the barrier to entry from team of PhDs to smart researcher with a laptop.
And that opens the door for preserving languages, for building translation tools for neglected dialects, and for understanding the universal grammar that connects us all. It allows the Wild West of unsupervised learning to actually be productive.
It's a hybrid approach that bridges the gap. It takes the black box of machine learning, the grammar induction, and guides it with the old-school wisdom of linguistics, the hierarchy.
It's the compass. You let the machine walk on its own, but you give it a compass so it doesn't walk in circles.
As we wrap up this deep dive, I can't help but think about what this says about our own brains. We tend to think of language as this impossibly complex web of rules and exceptions.
It feels that way when you're trying to learn French or German in high school.
Oh.
All those tables of conjugations.
Oh, absolutely. But this paper suggests that maybe, at its core, language is simpler than we think.
How so?
Well, if a computer can parse a sentence just by knowing that verb beats noun, maybe that's all we're doing deep down. Maybe our brains aren't running complex probability calculus every time we speak. Maybe we just have an instinctive ranking system.
That's a provocative thought. We don't learn the rules, we just learn the rank. We learn who the boss is.
It certainly suggests that hierarchy is more fundamental to communication than we realized, something to mull over the next time you're trying to string a sentence together. Just find the verb, and everything else will fall into line.
Thanks for listening to The Deep Dive.
See you next time.